Hello friends, during our discussion on Ampere's law and solenoids, the learning objectives would be to apply Ampere's law to a loop that encircles current. With Ampere's law, use a right-hand rule for determining the algebraic sign of an encircled current. For more than one current within an Amperian loop, determine the net current to be used in Ampere's law. Apply Ampere's law to a long straight wire with current to find the magnetic field magnitude inside and outside the wire, identifying that only the current encircled by the Amperian loop matters. Describe a solenoid and sketch their magnetic field lines. Explain how Ampere's law is used to find the magnetic field inside a solenoid. Ampere's law. We can find the net electric field due to any distribution of charges by first writing the differential electric field due to a charge element and then summing the contributions of electric field from all the elements. However, if the distribution is complicated, we may have to use a computer. Recall, however, that if the distribution has planar, cylindrical or spherical symmetry, we can apply Gauss law to find the net electric field with considerably less effort. Similarly, we can find the net magnetic field due to any distribution of currents by first writing the differential magnetic field due to a current length element and then summing the contributions of magnetic field from all the elements. Again, we may have to use a computer for a complicated distribution. However, if the distribution has some symmetry, we may be able to apply Ampere's law to find the magnetic field with considerably less effort. This law, which can be derived from the Biot-Savart law, has traditionally been credited to Ampere, for whom the SI unit of current is named. However, the law actually was advanced by English physicist James Clerk Maxwell. The integral form of Ampere's law is cyclic integral of B dot ds is equal to mu 0 multiplied by I encircled. The loop on the integral sign means that the scalar, or we can say dot product, is to be integrated around a closed loop called an Amperian loop. The current I encircled is the net current encircled by that closed loop. Application of Ampere's law. Let us first apply Ampere's law to the general situation as shown in this figure. The figure shows cross sections of three long straight wires that carry currents I1, I2 and I3 either directly into or directly out of the page. An arbitrary Amperian loop lying in the plane of the page encircles two of the currents but not the third. The counterclockwise direction marked on the loop indicates the arbitrarily chosen direction of integration for equation A. To apply Ampere's law, we mentally divide the loop into differential vector elements that are everywhere directed along the tangent to the loop in the direction of the integration. Assume that at the location of the element, the net magnetic field due to the three currents is vector B. Because the wires are perpendicular to the page, we know that the magnetic field at differential element due to each current is in the plane of the figure. Thus, their net magnetic field at differential element must also be in that plane. However, we do not know the orientation of magnetic field within the page. In figure, magnetic field vector is arbitrarily drawn at an angle theta to the direction of differential element. The scalar product on the left side of equation A is equal to b cos theta ds. Thus, Ampere's law can be written as cyclic integral of b dot ds is equal to cyclic integral of b cos theta ds, which comes out to be equal to mu 0 into I encircled. We can now interpret the scalar product as being the product of a length ds of the Amperian loop and the field component b cos theta tangent to the loop. Then we can interpret the integration as being the summation of all the products around the entire loop. When we actually perform this integration, we do not need to know the direction of magnetic field before integrating. Instead, we arbitrarily assume magnetic field to be generally in the direction of integration. Then we use the following curled straight right hand rule to assign a plus sign or a minus sign to each of the currents that make up the net encircled current. Curl your right hand around the Amperian loop with the fingers pointing in the direction of integration. A current through the loop in the general direction of your outstretched thumb is assigned a plus sign, and a current generally in the opposite direction is assigned a minus sign. Finally, we solve equation B for the magnitude of magnetic field. If B turns out positive, then the direction we assumed for magnetic field is correct. If it turns out negative, we neglect the minus sign and redraw magnetic field in the opposite direction. Net current. With the indicated counterclockwise direction of integration, the net current encircled by the loop is I encircled is equal to I1 minus I2. Current I3 is not encircled by the loop. We can then rewrite equation B as cyclic integral of b cos theta ds is equal to mu 0 into I1 minus I2. You might wonder why, since current I3 contributes to the magnetic field magnitude B on the left side of equation C, it is not needed on the right side. The answer is that the contributions of current I3 to the magnetic field cancels out because the integration in equation C is made around the full loop. In contrast, the contributions of an encircled current to the magnetic field do not cancel out. We cannot solve equation C for the magnitude B of the magnetic field because for the situation of figure on the left, we do not have enough information to simplify and solve the integral. However, we do not know the outcome of the integration. It must be equal to mu 0 into I1 minus I2, the value of which is set by the net current passing through the loop. We shall now apply Ampere's law to two situations in which symmetry does not allow us to simplify and solve the integral, hence to find the magnetic field. Magnetic field outside a long straight wire with current. Figure shows a long straight wire that carries current I directly out of the page. This equation for magnetic field due to a current in a long straight wire B is equal to mu 0 I divided by 2 pi r tells us that the magnetic field produced by the current has the same magnitude at all points that are the same distance r from the wire. That is, the field has cylindrical symmetry about the wire. We can take advantage of the symmetry to simplify the integral in Ampere's law if we encircle the wire with a concentric circular Amperian loop of radius r. The magnetic field then has the same magnitude B at every point on the loop. We shall integrate counterclockwise so that differential element has the direction shown in figure. We can further simplify the quantity b cos theta in equation b by noting that magnetic field is tangent to the loop at every point along the loop, as is differential element. Thus, magnetic field and differential element are either parallel or antiparallel at each point of the loop, and we shall arbitrarily assume the former. Then at every point the angle theta between magnetic field and differential element is 0 degree. So cos theta is equal to cos 0, which is equal to 1. The integral in equation b then becomes cyclic integral of b dot ds is equal to cyclic integral of b cos theta ds, which is then equal to b cyclic integral of ds, which comes out to be b into 2 pi r. Note that cyclic integral of differential element is the summation of all the line segments around the circular loop. That is, it simply gives the circumference 2 pi r of the loop. Our right hand rule gives us a plus sign for the current in figure. The right side of Ampere's law becomes plus mu 0 into I, and we then have b into 2 pi r is equal to mu 0 into I, or b is equal to mu 0 I divided by 2 pi r. Magnetic field inside a long straight wire with current. Figure shows the cross section of a long straight wire of radius r that carries a uniformly distributed current I directly out of the page. Because the current is uniformly distributed over a cross section of the wire, the magnetic field produced by the current must be cylindrically symmetrical. Thus, to find the magnetic field at point inside the wire, we can again use an Amperian loop of radius r, where now small r is less than capital R. Symmetry again suggests that magnetic field is tangent to the loop. So, the left side of Ampere's law again yields cyclic integral of b dot ds is equal to b into cyclic integral of ds, which is equal to b into 2 pi r. Because the current is uniformly distributed, the current encircled by the loop is proportional to the area encircled by the loop. That is, I encircled is equal to I into pi small r square divided by pi into capital R square. Our right hand rule tells us that I encircled gets a plus sign. Then Ampere's law gives us b into 2 pi r is equal to mu 0 I into pi small r square divided by pi capital R square, or b is equal to mu 0 I divided by 2 pi into capital R square whole divided by small r. Thus, inside the wire, the magnitude of magnetic field is proportional to small r, is 0 at the center, and is maximum at small r is equal to capital R, that is the surface. Solenoids. We now turn our attention to another situation in which Ampere's law proves useful. It concerns the magnetic field produced by the current in a long, tightly wound helical coil of wire. Such a coil is called a solenoid. We assume that the length of the solenoid is much greater than the diameter. Figure shows a section through a portion of a stretched out solenoid. The solenoid's magnetic field is the vector sum of the fields produced by the individual turns that make up the solenoid. For points very close to a turn, The wire behaves magnetically, almost like a long straight wire, and the lines of magnetic field that are almost concentric circles. Figure suggests that the field tends to cancel between adjacent turns. It also suggests that at points inside the solenoid and reasonably far from the wire is approximately parallel to the solenoid axis. In the limiting case of an ideal solenoid, which is infinitely long and consists of tightly packed turns of square wire, the field inside the coil is uniform and parallel to the solenoid axis. At points above the solenoid, such as P, the magnetic field set up by the upper parts of the solenoid turns, marked by dots, is directed to the left and tends to cancel the field set up at P by the lower parts of the turns, marked by crosses, which is directed to the right. In the limiting case of an ideal solenoid, the magnetic field outside the solenoid is zero. Taking the external field to be zero is an excellent assumption for a real solenoid if its length is much greater than its diameter, and if we consider external points such as point P that are not at either end of the solenoid. The direction of the magnetic field along the solenoid axis is given by a curled straight right hand rule. Grasp the solenoid with your right hand so that your fingers follow the direction of the current in the windings. Your extended right thumb then points in the direction of the axial magnetic field. The figure here shows the lines of magnetic field for a real solenoid. The spacing of these lines in the central region shows that the field inside the coil is fairly strong and uniform over the cross section of the coil. The external field, however, is relatively weak. Let us now apply Ampere's law to the ideal solenoid using the rectangular Amperian loop ABCDA. The magnetic field is uniform within the solenoid and zero outside it. We then write cyclic integral of B dot ds is equal to sum of four integrals, or as given by this equation. The first integral on the right of equation D is BH, where B is the magnitude of the uniform field inside the solenoid and H is the length of the segment from A to B. The second and fourth integrals are 0 because for every element ds of these segments, magnetic field either is perpendicular to ds or is 0, and thus B dot ds is equal to 0. The third integral, which is taken along a segment that lies outside the solenoid, is 0 because B is equal to 0 at all external points. Thus, cyclic integral of B dot ds is equal to BH for the entire rectangular loop. The net current encircled by the rectangular Amperian loop is not the same as the current I in the solenoid windings because the windings pass more than once through this loop. Let N be the number of turns per unit length of the solenoid, then the loop encloses NH turns and I encircled is equal to I into NH. Ampere's law then gives us BH is equal to mu 0 into I N H, or B is equal to mu 0 into I N. Although we have derived the equation for an infinitely long ideal solenoid, it holds quite well for actual solenoids if we apply it only at interior points and well away from the solenoid ends. This equation is consistent with the experimental fact that the magnetic field magnitude B within a solenoid does not depend on the diameter or the length of the solenoid, and that B is uniform over the solenoidal cross section. A solenoid thus provides a practical way to set up a known uniform magnetic field for experimentation, just as a parallel plate capacitor provides a practical way to set up a known uniform electric field. So friends, here we come to the end of our discussion in this lecture today, and therefore we sum up. In classical electromagnetism, Ampere's circuital law, discovered by Ampere in 1826, relates the integrated magnetic field around a closed loop to the electric current passing through the loop. A solenoid is a coil wound into a tightly packed helix. It refers specifically to a long, thin loop of wire, often wrapped around a metallic core, which produces a uniform magnetic field in a volume of space when an electric current is passed through it. A solenoid is a type of electromagnet when the purpose is to generate a controlled magnetic field. So that is it for today. See you in the next lecture, where we shall be discussing more about magnetostatics. Thank you very much.